AVL trees. AVL tree is a self-balancing binary tree. It was invented by J.M. Edelson Whiskey and E.M. Landis in the year 1962. The tree is named AVL in the honor of its inventors. In the AVL tree, the height of the two subtrees of a node may differ by at most 1. Due to this property, the AVL tree is also known as a height-balanced tree. The key advantage of using an AVL tree is that it takes 0 log n time to perform search, insert and delete operations in an average case as well as the worst case because the height of the tree is limited to 0 log n. The structure of an AVL tree is same as that of a binary tree, but a little differences there are. In its structure, it shows an additional variable called the balance factor. Thus, every node has a balance factor associated with it. The balance factor of a node is calculated by subtracting the height of the right subtree from the height of the left subtree. So, left minus the right subtree height gives the balance factor. A binary search tree in which every node has a balance factor -1, 0 or 1 is called as a height balanced tree. A node with any other balance factor is considered to be unbalanced and it requires rebalancing of the tree. Balance factor is equal to height of the left subtree minus the height of the right subtree. If the balance factor of the node is 1, then it means that the left subtree is one level higher than the right subtree. So if the balance factor is 1, that means the left is higher one level than the right. Such a tree is called left-heavy tree. If the balance factor of the node is 0, that means the height of the left subtree is equal to the height of the right subtree. If the balance factor of the node is -1, that means that the left subtree is one level lower than the right subtree. Therefore, it is called as right-heavy tree. So, note that the nodes 18, 39, 54 and 72 have no children. So, their balance factor is 0. So, because the nodes 18, so where is 18? This is 18. It has no children. So, right subtree minus left subtree will be 0 minus 0, that is 0. Even 39 has no children. So, again it will be 0 minus 0, that is 0. Even 72 has no children. So, 0 minus 0 is 0. 54 also has no left and right. So, 0 left, 0 right. That answer comes out to be 0. So, their balance factor is 0. So, next let's see for node 27. It has one left child and it has 0 right children. So, what will be? Balance factor is nothing but left height minus the right height. So, in the left it has one node. So, 1. In the right it has no. So, 0. So, balance factor is 1 for 27. So, the height of the left subtree is 1, whereas the height of the right subtree is 0. Therefore, the balance factor is 1 for 27. Similarly, we will be looking at 36. So, for 36, if we see, for 36 has how many right children? Sorry, left children, 2 left children. Left minus right, 2 left children are there. That is 27 and 18. Minus right is only 39. So, how many? 1 right is there. So, balance factor is 2 minus 1, that is 1. So, the left subtree has a height of 2, whereas the right subtree has a height of 1. Thus, the balance factor is 2 minus 1, which is 1. Similarly, the balance factor for 45. 45 is the root node. So, root node has 36, 27 and 18. How many left are there? 3 minus. Right is 63 and 72. That is 2 right are there. So, left height minus the right height. 3 minus 2 is 1. So, 45 has a balance factor of 1. So, the explanation is similarly the balance factor for 45 will be 3 minus 2, which is equal to 1. For 63, the balance factor is 0. Why? Because there is balance factor is height of left minus the height of right. Height of left is 1 because only 54 is present. That is, one element is present. Height of right is 1 because only 72 is present. So 1 minus 1 is 0. So balance factor for 63 is 0. Now look at the figures which shows AB, which show a right heavy AVL tree and a balance tree. So we will see this part now. Which one is right, which one is left, and which one is balanced. So first we will see that A, they are saying that it is left heavy AVL tree. Why left heavy? Because you can clearly see that the number of nodes in the left subtree are greater than the right subtree. So it is left heavy. Second is right heavy because the number of nodes in the right subtree are greater. And next is the balanced tree because there are equal number of nodes in the right and the left subtree. The trees given are typical candidates of AVL tree because the balance factor of every node is either 1, 0 or minus 1. However, insertions and deletions from an AVL tree may disturb the balance factor of the node and thus rebalancing of the node will be done. The tree is rebalanced by performing rotations at the critical node. There are 4 types of rotations: left left, right right, left right and right left rotation. The type of rotation that has to be done will vary depending on a particular situation. In the following section, we will discuss insertion, deletion, searching and rotations in case of a AVL tree. So I will take one example. Example is, consider an AVL tree and insert 18 into it. How do I go? So the AVL tree which is given, the question is 45, 36, 63, 27 and 39. So you have to insert what? Insert element 18. So how will you insert? For according to the BST rules, 18 is less than 45, so it would be to the left of 45, lesser than 36, left of 36, lesser than 27, to the left of 27. So the new tree will be 45, 36, 27, then you have 18, then you will have 39 and 63. So balance factor will be 1, 2, 3. 3 minus, this is what? 1. So 1, that is 2. Balance factor of root node is 2. Balance factor of 63 will be 0 minus 0, which is 0 for this. 39, it is a leaf node, 0 minus 0, 0. 18 is a leaf node, 0 minus 0, 0. 27 will be 1 left minus 0 right, which is 1. For 36, 2 left minus 1 right, that is 1. So my critical node is the root node. Critical node. Why? Because the balance factor is not in the range of 0, 1 and minus 1. So now I will perform the rotation. How will I perform the rotation? I will perform the left to left rotation. In the left rotation, what will happen? My 36 will come up to the left of 36. You will have 27 because I will only take this into consideration. To the right you will have 45. 45 right you have 63. 27 left you have 18. Element which is remaining is 39. Now 36 is greater than 39. So 39 will be to the right of 36. 39 is smaller than 45. So it will be to the left of 45. Now if you see, this is the root. So balance factor is 0. Balance factor is 0. Balance factor is 0. Balance factor for this will be 1 minus 1, that is 0. 1 minus 0, that is 1. 1, 2 and 1, 2. 2 minus 2, that is 0. So this is a balanced ABL tree. So which rotation we have performed? We have performed left, right, left, left rotation. We have performed which rotation? We have performed the left, left rotation. We will see the next example for right, right rotation also. So I hope this is clear. This was which rotation? Left, left rotation. So I will say one more example. Question 2 says, consider the ABL tree and insert 89 into 8. So you have this as 45, 36, 63, 54, and this is 72. So what I have to do? I have to first check the balance factor. Balance factor of leaf node is 0, 0 and 0. This will be right is 1, left is also 1. So left is 1 minus 1, that is 0. Left is 1, right is 1, 2. So this is minus 1. So this is a balanced ABL tree. Now in this balanced ABL tree, I want to insert element 89. So how will I do it? 45, 36, 63, 54, 72. 89 is greater than 45, so to the right of 45. 89 is greater than 63, to the right of 63. 89 is greater than 72, to the right of 72. Now I will check the balance factor. For leaf node it is 0, 0, 0. This will be 0 left minus 1 right, that is minus 1. 0 left minus 2 right, that is minus 2. And 1 minus 3, that is minus 2. Sorry, this will be 1 minus 2 because 54 is there. So left is 1 minus 2. So this will be minus 1. Now I will perform the right rotation. R rotation. So when I perform the right rotation, what do I get? I get 63 on top. 45 is lesser than 63. So left child of 63, 72 is greater than 63. Right child of 63. Then to the right you have 89. Then 36. 36 is less than 63. It is less than 45. So 36 will be left of 45. And 54. 54 is lesser than 63. 54 is greater than 45. So it will be to the right of 45. So now again I will check the balance factor. For leaf node it is 0, 0, 0. For this it is 1 minus 1, that is 0. For root it is 1, 2 minus 2, that is again 0. For 72 it is 0 minus 1, that is minus 1. So the balance factor is in the range of 0, 1 and -1. So we say that it is a balanced ABL tree. Next we will see the next two types of rotations, that is LR and RR. So we will take one example. Consider the ABL tree and insert 37. So this is 45, 36, 63, 27 and 39. Balance factor 0, 0, 0, 1 minus 1 is 0. For root it will be 1, 2 minus 1, which is 1. So it is balanced. Now they are saying that I have to insert what? I have to insert 37. Insert 37. So how will I do that? 45, 36, 63, 27 and 39. 37 is lesser than 45, so to the left of 45. 37 is greater than 36, to the right of 36. 37 is lesser than 39, so to the left of 39 you will have 37. Now balance factor will be 0, 0, 0. 1 minus 0 is 1. This will be 1 minus 2, which is minus 1. This root node will be 2. One, that is plus 1, and this will be 0. So again this one, after inserting also, it is balanced ABL tree. So next do a question on